Absolutely. Let's break down this physics material about induced EMF of electromotive force and current. Key concepts and formulas. Faraday's law of induction. A changing magnetic field linked with a coil induces an electromotive force, EMF, in the coil. Mathematically, E equals d phi dt, where E is the induced EMF, d phi is the change in magnetic flux, dt is the change in time. Magnetic flux, phi, a measure of the amount of magnetic field lines passing through a given area. Phi equals Ba cos theta, where B is the magnetic field strength, A is the area of the loop, theta is the angle between the magnetic field and the normal to the loop. Induced current, I. The EMF induced in a coil can drive a current through the coil if it's part of a closed circuit, has resistance. I equals E by R, Ohm's law, where R is the resistance of the coil. Lenz's law. The induced current will flow in a direction that opposes the change in magnetic flux that produced it. The negative sign in Faraday's law reflects Lenz's law. Explanation of the material. 1. Expressions for induced EMF. The material provides two ways to express induced EMF. E equals dash d phi slash dt. This is the calculus form, representing the instantaneous rate of change of magnetic flux. E equals phi slash d. This is the average form, where phi and phi are the initial and final magnetic flux values, respectively, and t is the time interval. For a coil with n turns, the induced EMF is multiplied by the number of turns. E equals n d phi dt, or E equals n of phi t. 2. Expression for induced current. Combining Faraday's law and Ohm's law, I equals ER, we get I equals d phi R dt. 3. Expression for charge. The material derives the expression for induced charge, Q, using the relationship between current and charge. I equals dq by dt. dq by dt equals d phi R dt. dq equals d phi as day R. 4. Note on resistance. Key point. Induced EMF itself does not depend on the resistance of the circuit. It's determined by the changing magnetic flux. However, the induced current and the induced charge do depend on resistance. A higher resistance will result in a smaller current for the same induced EMF. Methods of producing induced EMF. The material outlines two primary ways to change magnetic flux and induce an EMF. 1. Changing the magnetic field, B. As stated, this was the basis of Faraday's experiments. If you alter the strength of the magnetic field around a coil, you change the flux and induce an EMF. 2. Changing the area, A, of the coil within the magnetic field. This is illustrated in the example of the loop PQRS being moved into a magnetic field. As the loop moves, the area exposed to the magnetic field increases, changing the flux and inducing an EMF. This specific case is called motional EMF. Motional EMF example, loop PQRS. Diagram. The diagram shows a rectangular loop of wire, PQRS, being moved with a velocity, V, into a uniform magnetic field, represented by the blue X symbols, indicating the field is going into the page. Change in area. In a small time interval dt, the loop moves a distance, V dt, and the change in area within the field is dA equals L asterisk V dt of, where L is the length of the loop. Change in flux. The change in magnetic flux is d phi equals B, dA equals BL, asterisk V dt. Induced EMF. Using Faraday's law, the induced EMF is E equals d phi dt equals BLV. Direction of current. Lenz's law, or Fleming's right-hand rule, determines the direction of the induced current. In this case, it's counterclockwise. PSRQP. Important points to remember. Motional EMF. The EMF induced due to the motion of a conductor in a magnetic field. Lenz's law, crucial for determining the direction of the induced current. The induced current creates a magnetic field that opposes the original change in flux. Let me know if you'd like any part of this explained in more detail or if you have any further questions.